Thank you for that introduction, Peter. And so Andy Campbell and I will jointly, in our allotted 10 minutes here, give you a very quick overview of the two of our presentations at the AVIP conference this year. And it covers the topic of risk and performance objectives and metrics. All right, so just want to emphasize that this is a super fast, few minutes summary of a multi-part workshop, and so we don't expect everyone to, absorb all the details, but we just want to have a quick, give you a quick overview, and most importantly, introduce you to a document, one of a series of documents that was published by the Association of Vapor Intrusion Professionals, specifically the design roadmap, and then mention a couple of the other ones, and also want to emphasize that we're presenting basically one way to do this, and it's not meant to be an exclusive, like this is how you have to do it. It's just one way to approach design. There may be, and I'm sure are, others that work well, but this is just to provide sort of the beginnings of a basis for design. All right, so we'll talk a little bit about risk objectives, define those, risk metrics, and then setting the numeric performance objectives, introduce you very quickly to the calculations, not going through them in too much detail, and then also touch on performance verification. And here on this slide, you can see the cover for this best practices guidelines that AVIP put together, and you can see the assistance from a lot of folks from a lot of different companies collaborated to put this document together. And so it does represent sort of an overview of best practices from a number of practitioners in the industry. And also, just to mention, there's a companion guidance document on operation and maintenance of these systems, and yet a third document also on construction quality assurance. And I would say all of those are equally important, but this one just focuses on the design. So what are risk objectives? The way we like to think about this is that the objectives are, of course, numerical, and generally there are two that we look at from a human toxicology standpoint. One is the excess cancer risk, and generally EPA and other agencies, look at it as a range of 10 to the minus 4 to 10 to the minus 6, so 1 in a million odds of developing a cancer that you might not otherwise develop in your lifetime, and the hazard index, which should be less than 1. And of course, important to always remember that if you have multiple constituents of concern, you need to sum all of those together. All right, and to give just an example here of applying the guidelines and going through the calculations, you need to know a lot of information before you get started. You need to have some idea of your concrete properties. We've included in our presentation just a couple of examples that we feel are sort of decent, if you will, values to assume to start with. You may have other, for example, specialty concretes, different permeability. So things to keep in mind. These are just examples. Gravel layer, we've assumed a certain thickness, a certain permeability, a certain porosity. Permeability, porosity probably hold true most of the time, but you might have a 6-inch gravel layer or a 12-inch gravel layer. So again, these are just examples for the calculations that Andy's going to go to in more detail. Your constituents of concern, of course, soil properties, depth of water, right? You might have a dry installation, or you might have, 5 feet below ground surface and counter groundwater table. So these are important things to know going into the design. And of course, building dimensions, and one of the key parameters that's sometimes tough to nail down early on is, for example, the typical ceiling height. And then, so here's just again plan elevation for a building, and calculated the cumulative risk and hazard index for this example. And again, Andy will go into more detail in his segment. And so, what we need to do is we need to translate these risk metrics of excess cancer and hazard index into an acceptable indoor air concentration for each of the constituents of concern. And I think a lot of folks are familiar with the concept of an attenuation factor, which is simply the ratio of the concentration in indoor air to the concentration in soil gas. And very simple graphic here. So you have concentration in soil gas, which then presumably attenuates, dilutes a little bit in the gravel layer, and then your COCs need to get through your vapor mitigation system, the membrane as well, and then it encounters the concrete. So there's multiple, right, steps along the way where the concentrations can be attenuated. But the sort of the gross attenuation captures all of that. So indoor air concentration to soil gas. And one of the things that we wanted to get across in our presentation is that risk drives performance. So in the previous graphic, you could see you have whatever concentration you have of your COCs and soil gas, and your performance objectives for the vapor intrusion mitigation system are set by what you need to get to for your concentrations in indoor air. So again, what is the performance for your membrane? What's the performance for that you can assume for concrete, and so on. So we're just looking at how well does the system need to perform in order to mitigate the risk that's presented by your COCs present in soil gas on your site. And so with that, I'll hand it over to Andy to go into the further details on this.
We are here to reduce risk. Your performance metric is generally whatever attenuation factor alpha you use to replace the EPA's default value of 0.03. Engineering controls like vapor barriers, that's one example, they give you a smaller alpha value. That's better, and it allows you to calculate a better risk metric with that additional protection. You can also have an attenuation factor for something like a ventilation system. But in that case, your calculations may or may not build in the 0.03 for the floor slab. It just depends on where your point of control is. Here's how you would calculate the attenuation factor for a vapor barrier using field data. Radon is a useful surrogate for doing this, and Glenn Tofani will talk more about that later on today. But before you ever get to the field, you will want to know how a vapor barrier should perform and what it will do. And we can calculate safety factors for some of these failure mechanisms that you see here. The reason we can't calculate for all of these failure mechanisms is because we don't know how large a membrane defect will be. That's this side of the grid. Those defects typically occur during construction, so you don't know yet, but we can calculate how big a defect can't be, and we call that the critical defect size. We don't have time to discuss all the math involved here, so we encourage you to obtain the presentation slides from the AVIP 2025 Wednesday workshop, where we go into more detail. Okay, now about performance metrics for subslab depressurization. In the workshop, Cheryl Carey and Elizabeth Wang of Catalyst Environmental Solutions explained that when you apply the concept of flux to VIMs, two kinds of flux cause VOC migration into the indoor environment. Advective flux is the transport of a substance through the bulk movement of the fluid that the substance lives in. That's these arrows. They act over an area. It's the physical transport of air with VOCs flowing from the subslab environment into indoor air. Pressure gradients drive advective flux. And then there's diffusive flux, the transport of VOCs down a concentration gradient. And in an environment of high concentration of a compound, and that's these orange dots you see below the slab, diffusion causes the compound to move into areas of lower concentration. And that's the other dots you now see above the slab. Diffusive transport occurs independent of pressure gradients or the net movement of matter. Michael Nemeth will elaborate on how that works in concrete, also later today. But to be 100% effective, an SSDS needs to overcome advective and diffusive flux. You need to know what amount of negative pressure is necessary to overwhelm all of that. And that's what these downward arrows represent. They're a counterflux, if you will. And if you can do it, you sever the exposure pathway. For severed exposure pathways, the attenuation factor becomes 0. Or with SSDS, you might end up just attenuating the vapors. You can calculate that too, but we don't have time for the math. So again, we recommend checking out the workshop materials from AVIP 2025. Alternatively, many regulators have their own performance metrics for this. It could be 1 Pascal of differential vacuum, 4 Pascals, or 10. Also, at the 2024 AVIP conference, Yogi Panda introduced a great spreadsheet model for predicting subslab vacuums. This is one way to determine if you're likely to achieve your performance metric throughout a new building subslab airspace. Or you could instead do a pressure field extension test for an existing building. And David Hanley will speak about those today. And we don't have enough time to calculate attenuation by subslab ventilation, but the AVIP 2025 workshop also covered that. And Yogi Panda will present some calculation methods about that today. Finally, in the workshop, Jonathan Sanders explains some methods of calculating indoor air ventilation. I threw in some more equations I've found helpful. Many of these parameters are actually available in the Johnson and Ettinger model guidance. So that's it for us, and we'll now move on to the next series. Thank you all.